So here we're going to talk about concavity and really try to get an understanding of what it means. Hopefully you've already watched the video on the second derivative. Here we're going to make some more connections between the second derivative and concavity, and then talk about something called the second derivative test. So if on this graph here we wanted to identify the intervals of positive concavity and negative concavity, how could we do that? Well, remember what that means. Positive concavity is like a graph that's curving in an upwards manner. And negative concavity is the graph is curving in a negative manner, or in a downwards manner. So, for example, this first region here, is this curving downwards or curving upwards? Well, if you look, it sort of looks like part of a parabola, right? And that parabola would sort of be opening downwards. So that's one way to think about concavity. It's like, is this section of the graph part of a downwards facing parabola or an upwards facing parabola? And in this case, as I said, let's do that in highlighter instead. There we go. So this part of the graph here is curved downwards, like a downward facing parabola. The next part of the graph, so this is sort of downwards. The next part of the graph here, is that opening upwards or opening downwards? Is it curving upwards or curving downwards? Well, if we look from here to here, it's like it's curving upwards. It looks like a positive parabola, right? And a positively or a parabola that's opening upwards. But then here we have a parabola that's opening downwards, right? So if we sort of zoom in on this region here, it's like we have a upwards facing parabola here, and it's like we have a downwards facing parabola here. Somewhere in between, the graph looks very flat, not curving at all, not concave at all. So we call those points of inflection. And that's usually what you get between, it's always what you get between a concave up and a concave down section. So in here, we have that point of inflection. So I'm going to erase these so we can see it a little bit clearer. But essentially what we have is, let me zoom back out so we can do that. We have a concave up section here, and then a concave down section here. Where does that change back to a concave up section? We know we have a concave up section here, right? It looks like a parabola that's opening upwards. So where does it change? This is the hard part for a lot of people, is identifying where it goes from a concave up to a concave down section. I'm just going to sort of zoom in to help me figure this out. So here, it looks like a parabola that's opening downwards. Does it still look like it's a parabola opening downwards here? Sort of. It sort of starts to curve the other way here. And if we move it over, you can see here, so here, curving downwards, and then here is where it starts to sort of curve upwards, like a upwards facing parabola. So the point of inflection is going to be somewhere in this region here. We don't know exactly where it's going to be. It's not going to be around the 0 because it still looks like a parabola facing down, but it's going to be sort of close to it. So I'm gonna make this line go here. So this, we'll say it continues to right about here, and then it switches to an upwards facing parabola. Does it ever change back to a downwards facing parabola here? Not really, it just sort of continues up like that. So that means we have another point of inflection right here. I'll call this one a POI, point of inflection, because I'm too lazy to write out the whole word. Okay, but you sort of see that, how that changes from a concave up to a concave down graph. One other way, if this sort of confuses you, in terms of looking at it in terms of like little parabolas that open up or down, you can also look at it in terms of circles, because concavity has to do with curvature. Concavity and curvature are two words that sort of mean similar things, but not exactly. But if you look at any part of the graph, you can sort of see, so with the first derivative, we're always looking for a tangent, like where 2 points are like tangent to the graph like that. But with concavity, we're looking at 2 points, and we're looking at sort of the circle that can be made between those 2 points. So in this case here, we would have a circle with a very large radius like this, right? And if you can continue that circle all the way around, blah, blah, blah. So the circle that's tangent to these 2 points would sort of look like that. And if you go up here to like these 2 points, the circle that we would be made with those 2 points, it's sort of like a tighter circle, maybe something along those lines. That was bad at the end, but that would be like that. So the curvature and the concavity, curvature just basically has to do with the radius of that circle, tells us a little bit about the concavity. And you'll notice if the circle is on top, like if the circle is above the graph, that means it's concave up. And if the circle is below the graph, it's concave down. So like for instance, if we were to draw a circle between these 2 points, so like the circle with that kind of deal like that, it would look like that. So that we know that's concave down. If we were to draw the circle between these 2 points of the graph, it sort of has this radius right here. So that's a little tight circle in there. Tiny little circle there. So that tells us also if it's concave up or concave down. The number that's associated with concavity, like whether the concavity is 5 or 10 or -2, has to do with the radius of that circle. So if it's a tight radius like this, it has a very high concavity because it's like curving a lot at that point. If it's a very large circle, like this over here between these 2 points would make a very large circle, that's going to be a very low concavity or low curvature, right? Because it's not curving very much at that point. And in between a positive and a negative section, you'll notice you have like a straight line at these points of inflection. So you can't really draw a circle when it's a straight line because the circle would be infinitely large. So we would essentially say that that's concavity of 0, which we know is another way to say it's a point of inflection. So anyways, concavity and circles are all related together. So we can just very quickly state our intervals of positive and negative concavity. Positive concavity are the red zones, so sort of between here and here. Let's just say that that's like -0.5. So we're going to say between -1 and -0, and -0.5. And also, actually I should leave out that second bracket, and then another region which is, I don't know, we'll call this 0.6, I don't know, 0.6, let's just call it 0.6, between 0.6, or actually just x is greater than 0.6. Okay, those are our red regions, our positive concavity regions. Our negative concavity regions are when x is less than -1, sorry, when x is less than -1, and then when it's between 0.5, -0.5, and we said this was 0.6, right? So when x is between -0.5, and 6, 0.6. Okay? So there we go. That's identifying concavity from a graph. Now, what can we infer about the second derivative in relation to concavity? I'm going to take out the other. What can we infer about the second? Yeah, and concavity. So we know from the previous video, you should understand that when it's concave down, the second derivative will be negative, and when it's concave up, the second derivative will be positive. So that's essentially what it is. So this is a region. Let me switch to red for a second. This is a region where the second derivative is positive. This is a region where the second derivative is positive. This is a region where the second derivative is negative. This is a region where the second derivative is negative. Okay? So you can summarize that in your own words, but essentially that's the case. I'll repeat it one more time just so you got it. When the second derivative is positive, the graph is concave up. When the second derivative is negative, the graph is concave down. Okay? In between those regions, when the concavity is, or the second derivative is equal to 0, you're at a point of inflection. Okay, so how is this useful to us? Why is this a useful thing to understand, other than just sort of knowing the curvature, how curvy the graph is, because that's essentially what it is. But how is this useful with where we're going in this course? Hint, it's going to be useful for sketching graphs of functions. It's actually going to be very useful for that. And that's what the second derivative test is going to help us with. But let's talk about how we've, up until now, found out whether points are maxima or minima. So this is the same graph. You'll notice this graph is similar to the one on the first derivative test. It's actually the exact same graph. I just wanted to use the same one to illustrate my point. So up until now, how can we tell if points are maxima or minima? So pretend we didn't have the graph. We have a function, and we've solved for the fact that the zeros the critical points, sorry, are at -1, 0, and 1. So this is the place where the derivative is equal to 0. So they could be maximums, they could be minimums, we don't know. I mean, we could look at the graph to test. But if we didn't have the graph, how could we check? So far we have two ways to do this. The first way to do this, to check if these points are minima or maxima, are plug in a value on either side, right? So plug in values into f of x on either side of the critical points, right? So what we would do is, if we know that, for example, at -1, there's a point on the graph, if we wanted to know if it's a maxima or a minimum, we can plug in a point on either side, and if it's lower on either side, you know it's a maximum, and if it's higher on either side, right, you know it's a minimum. So if these are our critical points, I'll call them CP for critical points, we can check it that way. That's the first way. The second way is to use the first derivative test. And that's where we set up a table, right, to check the values between those critical points, to check the derivative between those critical points, right? So what we would do is, if the critical points were -1, 0, and 1, we would basically set up a table like this for f prime of x, right, the derivative, and we would see whether the graph is positive or negative between there. So it could be like positive, positive, negative, positive, something like that. And that would tell us that between these 2 points, the graph is increasing and then increasing, and then it's decreasing and then it's increasing. So that tells us that there's a maximum here and that there's a minimum here. If you're confused about that, go back to the video on the first derivative test, but that's essentially what it was. We actually have one more tool, a third way to check if a point is a maximum or minimum, and that's the second derivative test. This is useful in some cases. It's not always useful. Sometimes the first derivative test is the best way. Sometimes just plugging points into the function is the best way. Sometimes the second derivative test is the best way. It's good to have all these separate tools in our toolbox because we don't know when each one is going to be useful. So, for example, going to our example, I should say, this is the function we're looking at. We know the critical points are -1, 0, and 1. How can we check if they're maxima, minima, or neither? We can do this by checking the concavity of the graph at those 3 points. Because what do you notice about the concavity of the graph at this point? Well, the concavity of the graph at that point is going to be 0, right? Because we call it I forgot about that. We actually have one more point of inflection here. Sorry, I missed this from the first part. Hopefully somebody caught it. Whenever we go, taking a step back, whenever we go from a concave down to a concave up, we have a point of inflection. So I actually missed that there was a point of inflection here. That we made that clear in the last video, but hopefully that doesn't confuse you. Whenever we change from concave up to concave down, so we have another point of inflection there. Okay, so in order to check whether these points are maxima or minima, so now going back to the second derivative test, for example, if we look at this point here, right, at 0, at x equals 0, what do you notice about the concavity of the graph there? Well, it's negative. When the concavity is negative and the slope is 0, we know the graph is going to look like this. It's going to be concave down. If the graph is concave down, that tells us it's going to be a maximum, right? And down here, similarly, we know at this point where the slope is 0, the graph is concave up. So that tells us right away, if the graph is concave up, it tells us it's got to be a minimum point, right? Because that's the shape of the graph at that point. So the second derivative test basically tells us, by looking at whether the graph is concave up or concave down at any given point, it tells us whether it's a maximum or a minimum. So all we essentially need to do to find out whether a point is a maxima or a minima is all we have to do is plug in to the second derivative. So we would do f double prime at, let's see, at -1, f double prime at 0, and f double prime at 1. So we essentially just check the concavity at each of these zeros. And if we plug this in, if we were to actually sort of take the second derivative, plug in these values, I'm not going to do that here because I know you can do that. This is just a polynomial. It's a little bit of a long polynomial, so I'm not going to do it. But I'll tell you that the second derivative at a -1 is 0 here. The second derivative at 0 is -12, and the second derivative at 1 is 48. Remember, these refer to the concavity of the graph. So here, for this first one, it's telling us that the concavity of the graph at that point is 0. So essentially, looking back at our graph, the concavity is 0, which means, remember, where the concavity is 0, or where the second derivative is 0, we call that a point of inflection. And if you think about our previous video again, when we have a point of inflection, that point is not a maximum or a minimum, right? It's just a point of inflection. The graph continues to increase on either side of this, or decrease, but in this case it's increase. If we plug in the double derivative at 0, we get -12. All that means is that the graph is a sad face. It's going downwards, it's opening downwards, right? It's got negative concavity at that point. So therefore, we know this is a maximum. And if we do the same thing, we plug in f double prime at 1, we know it's positive 48. So the graph is a smiley face. And when that's the case, we have a minimum. Notice these are local maxima or minima. To find the global maxima or minima, we need to check all the points on the graph and the domain. But essentially, this tells us right away whether it's the graph opens up or down, so it tells us right away whether it's a maximum or a minimum value. So the second derivative test is nice because you only need to evaluate at those critical values, right? If you plug in those values, it's going to tell you if the graph curves down or curves up. So you don't need to make a fancy table, or you don't need to do anything like that. So when do you think each one of these methods for determining maxima or minima is going to be useful? When is it useful to just plug in values? When is it useful to use the first derivative test? When is it useful to use the second derivative test? All of them work, right? But I would argue if it's really easy to find the second derivative, like if it's simple to do, if you're just working with a polynomial that doesn't have huge numbers, the second derivative test is probably the most straightforward, right? Just take the second derivative and plug in a few points. It has the added bonus of this: when it's a polynomial, the second derivative is always simpler than the first derivative or the original function, right? Because you sort of knock off terms as you take more and more derivatives. So the second derivative test can sometimes be a very quick way to check to see if points are maxima or minima. On a test or quiz, it'd be up to you to figure out what the best way is. If I gave you a question like this, it would be up to you to figure out what the best way to do it was. So hopefully you understand that second derivative test. When the second derivative is 0, it's a point of inflection. When the second derivative is negative, the graph will have a maximum at that point. When the second derivative is positive, it will be a minimum at that point. You can summarize that yourself in your own words. Okay? There you go.